Welcome, inter integral calculus exam review. In integral calculus, we had two lessons. One is review of integrals, and one about integral function, which is important for infinite series solutions. Uh, in this lesson, we learned that integration is the inverse operation of differentiation. So if I have a derivative of a function, if I integrated this derivative, I will get uh, my original function, but I cannot retrieve every part of the function, especially like the constant part. So the constant could be 1, could be 4, could be 8. So I don't know what was this constant, so I just put a constant. Yeah, I add an integral to account for a constant. Uh, and we have seen an example for this. So this may be my original function. That's the derivative of this function. If I integrated this, I will get this plus a constant. How could I know this constant? If I have some initial condition, boundary condition, or whatever, then I can substitute it and like figure out what this constant is. Yeah. Uh, and this rule, so that's the integration rule, that's good for every case except that like n is equal, does not equal to -1. Yeah. We also learned about this is called like indefinite integral. We also learned about a definite integral where we integrated from an interval, like from a to b, like a is equal to 10, b is equal to 12. So I integrate this from a to b, then I substitute my integration like limits here 10 and 12, then I can find like evaluate, for example, like the area under the curve, or I could length of a curve, or whatever like I'm solving for. Okay, so in that case, like the area under the curve, that would be the integration, like the area under this curve, like function number one, and that's all the way to the end. If I have another curve here and I want to find the area between these two curves, then like let's say I have another curve here, and then I want to find like this area between these curves. So how can I solve this? So basically, if I calculated the area under this curve and subtract it from the area under this curve, which is like this one, then I will get like this area here. Yeah, that's basically like how to do it if there are two functions. Okay, so we can find the average value of a function at an interval, like you can use this equation. We have also learned about integral of commonly used function. So 1 over x, for example, that would be like len x, and so on, logarithmic function, trigonometric function. So, and again, I showed you in the previous exam review, there are tables. You can print this table with you. It's very handy. It's just one paper you want to print. It's very handy to have it with you. If you need me to print it for you, please let me know and I can print it for you. Yeah, if you don't have a printer. But that's very handy to have it because these are easy problem and easy point. We also integration with a constant. Like if you have a constant here, you can just take it out because anything time a constant, like a constant time anything, like you can just take it out and just multiply whatever you have by this constant. A separation of term, we've learned this, like you can integrate this part and this guy here. Integration by recognition, so that is like, that's not, that's common also. Like, so I see a function, yeah, and then I see the derivative of this function. So that would be the len of this function plus a constant. So, and sometimes you don't have the exact derivative of a function, but like maybe if you added a constant to it, or like multiply by constant or divide by constant or whatever, then you will get the derivative of this function. So in that case, like you add this constant and then you find the derivative of the function and then you multiply or divide here by this constant. And then we also learned about the integration by part. So that is also something you can check. Yeah. So you have like U and dv, and then that's basically takes this form, and then you can do the integration by part. So I give you here like the exam will have something like this. So if you can solve something like this, then you should be able to solve the exam. Again, you can have it, you can print, you can have all this printed, and that would be like easy point. Like, so you look at something like this, okay, you know, I raise this to the power of 3, then I divide by 3, then I got like 3x. I got something here like this. This is a constant 1 over 4. I take it out. This is x to the power negative 2. Then I add 1, and then I multiply by negative 1. So that would be like negative 1, and then I divide by like negative ones, and I get a negative, and then I get like 1 to the power 4. And same here, and same here, and same here. You just like see the rule and try to follow it. Yeah, so you can have something like this here, and then that would be like this term plus this term plus this term plus a constant. Again, in the final exam, it will not look like this to be multiple choice. So maybe I will give you something like this, and I will give you different answer, and then you have to choose a correct answer. We also learned about the separation of terms. So like if I have something like this, then what I can do is that I can do like separation of terms. So I can get like one term here like as 1, for example, and another term here as something like that looks like this. And this is like integration by recognition, for example, like this part, like that's integration by recognition, that's like regular integration. And but like in order to move from this form to get it into this form, you have to remember from algebra like long division. So like the long division, what you do here, like you divide it like your numerator by your denominator, and so basically like you divide like this guy here, you get like you get like 1, and then like you subtract here, like you get the remainder, and then you will get like a form that looks like this. Yeah, and then you can check it back, like if you multiply this times this and add it to this, like you'll get this original form. And if you want to see like these steps in details, please go back to the slides. At the slides also, below the slides there are notes, so try to check also the, let's see, like there are always like I put notes, so check the slide notes, and you will learn more about like integration by division. So here, this is like an example of practice. So try to do this problem. Again, the exam would be something similar. So if you can do this practice problem, the exam would be similar. Integration by part, that's like used to integrate the product of two function, and how to choose, like the integration by part is usually how to choose the ux and the vx, and that is the rule, how to choose the u and dv. Helpful guideline, like always start like the logarithmic function, inverse trigonometric function, algebraic function, trigonometric function, and exponential function when you select the u, and prioritize functions that appear in this like order. So if you have log x or len x, that should be your u, and the other part of your functions, that should be your v. Yeah. So here, this is like more practice of of this integration by part. So like here, that's, you don't need integration by part. Here you don't like, you don't need it here. This is integration by recognition. Like, so like, what is the derivative of x squared plus 2? That's 2x. But here I only have x, so I need to divide by, so I need to like add a 2 here, and then like divide it by 2 here. So like, see this part, like I have like this guy here. The derivative of this guy is like 2x, but now I have only x here. So what I can do, I can just add 2x here and then like divide it by 2, because like 2 will go with the 2. Then I can do like integration by recognition. Here you just like follow the rule. Here I can do integration by part, yeah. And here are the steps, yeah, if you want to do like integration by part. Okay. We also learned about higher order integration. So higher order integration, basically you so here I am integrating dx from 0 to 4, and I'm integrating from dy from 0 to 3. It doesn't matter which order it is, like I can get this out and then like get this out and then get this in and get this in. Doesn't matter like how order, but it just matters that like when you integrate with the respect to x, you treat everything else as constant. So the y will be constant and the 2 will be constant. And then when you integrate with respect to y, you treat x as constant. So again, try to solve these problems. You have a few, like your homework problem, you have some exercise problem, you have some practice problem. If you can do this, then it should be easy. Yeah, you can easily like solve these types of problems. Yeah. We also learned another lesson, which is so that's mainly like a review of what you did before in Calc 1 and Calc 2. Yeah, integral functions, that's an important topic because some the some of the differential equations, or you can they don't have like an analytical, like they don't have a closed form analytical solution. So if they don't have a closed form analytical solution, you can either do an infinite series solution or a numerical solution. Yeah. Uh, so the integrations that cannot be presented by closed form solution can be presented by an infinite series. And that is based on the concept of like Taylor series expansion and the Maclaurin series. So for example, I can approximate an exponential function by this series. Yeah, so that's like an exponential function. I can approximated by this series. So integral functions just as like the exponential function, for example, error function that's used, for example, like when you find like contaminant transport equation, friction dispersion equation, it's expressed as error function, gamma function, Euler constant, many types. Like when you have complex boundary, we generally express this by an infinite series solution. So for example, like the integral exponential function has no closed form solution, but has an infinite series solution as defined by this. So if I have like an exponential function and I want to integrate it, it has no closed form solution, but it has an infinite series solution that takes this form basically. Yeah. So here, like I'm doing, this is like a dummy variable, and here I am integrating from x to like positive infinity. I could also integrate from negative infinity to x, and then you get the solution. And we've seen an example like the drawdown can be presented by this equation. So basically, it can be presented by an integral function, something that looks like this. And like you have the u, like you can express it by these parameters. And basically, like I want to do this integration. So this integration, basically, if I want to do it, it will take this form here. So here, that would be the Euler constant, negative len x, and blah, blah, blah. Okay, so if this one, it has a solution, and that solution would look something like this. So that's the exponential functions. That's the solution of the exponential function. And then I can like replace this guy with like this exponential function, and this exponential function would look something like this. So that's the Euler constant, negative len. So here I'm integrating from u to infinity. U is given by this, so this is like len u plus u, like this term, like u squared, and so on and so forth. 2 times the factorial of 2, 3 times the factorial of 3. And then basically you need to see like how many terms you want to retain. The more term you retain, the more accurate the solution will be. Okay. So anyway, the more accurate the solution will be. So basically you just, I mean, these problems are easy. You just substitute something here, like you calculate the infinite like series solution, you substitute it here and then you can calculate your x. And then I give you like a problem, for example, like everything is giving, like q is giving, t is giving, s is giving, and I'm telling you like what is the drawdown after 1 year, so you can calculate the u, and then you have like this wu function, which is like this. In groundwater hydrology, we call this exponential function like well function, but it is same. It is the same. This is the same as this one. Yeah. Here. So basically, like what you can do, like you can calculate the u, and then you have this u, you substitute this u here, like so you substitute like this guy here, substitute this guy here, you substitute this guy here, then you get this one, and then you can calculate like as a drawdown function. So homework, infinite series solution drawdown can be presented by this, where u is giving like this, and here I'm explaining all these terms if you want to learn about it. The solution of this equation is given by the exponential function, where this exponential function is this. So the above solution, what is the above solution? It's an analytical solution, closed form solution. Is this correct? No, it's not a closed form, because I have like this infinite series. Analytical solution, infinite series solution, yes. So this is wrong. I mean, it's an analytical solution, but it's not a closed form solution. It's an analytical solution and it's infinite series solutions. Numerical solutions, that's not a numerical solution, that's not a numerical. Quadratic rule, trap rule. There's no such thing as trap rule. This is basically a trap for the student who didn't study the lesson. Yeah. But anyway, so that's, I think that's all for this. The main thing here, practice these problems. If you practice these problems, like for example, like here, just practice, for example, how to uh, for example, like I don't know what will the final exam include, but just practice, like if you're giving a problem like this, how you can calculate like the u or the x or whatever, substitute it here, calculate like your infinite series, and back substitute here and calculate your x. Most importantly is that you know the basic concept, that this is not a closed form solution as we did before, but this is an infinite series solution. Yeah, something like that. So that's basically what it is. Okay, so that's